start my second lecture, which is on regulation signal. By the way, this is a part of real-world data analysis that is in program students and also students from graduate schools of engineering and probably informatics. So in the last lecture, we discussed denoising because every signal, every data that we measure from the real world cannot be free from noise. So denoising is very important and fundamental. And this lecture will introduce a regulation, which is how to do inference from the data, which social inference is a variable which potentially be associated with observing data, but not easily observed time or in online manner. So this is a typical figure of what is regulation. So we do have two variables here. One is the original independent variable, and the other one is the dependent variable, which is related to the dependent variable. And suppose that we can easily measure or observe these data, but you cannot observe this, the second axis variable on real time or simultaneously. Then problem is how we can estimate the value of the second variable when you given the first variable or set of first variables. Those problem is called the regression problem. Well, in Chinese, it should be written in Chinese character, kaiki. So in this lecture, I'm going to talk about this first. I'm going to move to the next topic, which is sequential data. But anyway, we defined what is a signal. Signal is a data set of variables, a set of data, which is indexed by integer number, which sometimes began from minus infinity, sometimes begin from 1 or 0, whatever, but associated with integer number. And this was an example that we have had a sequence of data of the Nagoya city population. And then we discussed about the trend and average and also logical fluctuation. And we discussed how to model the data. And in this presentation or lecture, I will try to explain how do we determine the model, which in the previous case was defined in terms of A1, A2, A3, blah, 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 which are the coefficients for constant term and also n term and also sine term. But anyway, independent data and dependent data, these two data are associated with kind of physical, kind of social, relation. That is, problems that we see behind this problem. So very simple regression is time series regression. like this. In this case, how do you guess the fourth number of this sequence of numbers when you gave the sequence like 3, 1, 4, and something, then 5? Then what is the guess? 2. Why?
Minus 2 plus 3, minus 2 plus 3,
Okay.
and so on.
So, yeah, probably you're correct. But my original intention was 1.
Why?
This is a sequence of pi 3, 1, 4, 1. So it can be something, okay? But when we given the sequence of data, we probably have to have what is sequence means, right? So, as you answered, we can define the sequence as a relative relationship to the foregoing number, to the current number. That is one definition. And the other definition is like that, sequence itself has something mean. But anyway, the regulation of signal is a problem to find the rule that generates the signal or the ordered data. This is a simple definition of a regulation in this case. And the rule is useful when it is represented by a mathematical form. In the original thought, I put 1 here, but it is not easy to write down the number as a function of order, like 1, 2, 3, 4, 5, because this is a sequence of a number, real number. So you can now write down easily by like this. Pi is a very complex number, not a complex number in the mathematical meaning, but. So when you can write the data like this, cosine 2 pi over 15 times n multiplied by 0.8, then you can easily expect what will be the number when n is 128, for instance. And this is not an easy case, but easy case is a combination of polynomials, probably. And finding the best form of the regression function is an open problem. Because if you knew the set of data or sequence of data, you cannot know what is happening, only those data. If you have some insight or basic understanding of the phenomena that you are observing, then you can make some hypothesis that this data and this data are somehow correlated or somehow, how do I say, associated with a rule like this. In this case, x and n are associated with this rule. And because what we are dealing with is natural data from the real world, that is observation. Therefore, you do not know this particular rule for generating this data. But at least you can hypothesize that this and this should be associated with this. And you can verify the rule, or you can optimize the rule by means of regression. So this is a very fundamental idea. One example is a moving point. Assume that m, which is point mass, moves in constant speed, which is 0.2 meter per second. This is physically a model, physical model, starting from 1.2 meter away from the original point. The displacement of the m after n second moving is given like this. 1.2, which is the original length or displacement, and every second the point will move to 0.2 meter farther than the original point. Therefore, this simple first order equation will give you the correct displacement of the point mass, m. So when you plot this relation, you can see like this in a discrete time case. And if n is continuous time case, which is n is involved in or included in a real set of data, then this becomes a simple line. Well, anyway, this is the hidden phenomena. And if you only observe that point movement of this mass, then probably what you get is not such simple, because you have to deal with real world data, which means that there are noise and error of observation are not be avoidable. So probably real world data is like this. It is not on the simple one line, but somehow has a trend that when the time is progress, then the displacement is also getting bigger. So if you see this, and suppose that you don't know what is happening physically, but if you see this, probably you may guess or hypothesize that the displacement at the end time point should be given like this, which is x0 plus v times n. In this case, v is the speed of the constant moving, right? Oh, that's not so much difficult, Or is more familiar this representation is y is a x plus v. This is first graphical representation to variable relation. Maybe we studied in high school. It is also saying, a is an speed and x is the first place displacement. x0 in this case corresponds to b here, and v is corresponding to a here, and small m corresponds to x. And y in this case is x times x increased by x. So you can somehow hypothesize this kind of thing. Then what should we do? What we should do is to define, to estimate or calculate theta 1 and theta 0. Those are the parameter of the model. So this is a model, and this is a parameter, and this is the data. So by using data, you're going to guess what is the parameter value. That is the estimation problem. And why? And when you solve that problem, in other words, you find the optimal theta 0 and theta 1, then you can plot this line, and this line gives you a regression of the data from theta like this. And finding the optimal theta 1 and theta 0 is a technical problem, but it is easily solved by a simple linear equation. That is very good news to us. I'm sorry, I did a very important presentation yesterday together with our president, which is a final review of the leading program efforts, and therefore I am kind of exhausted. with that. So this lecture will be not really
してしまうと、反価誤差がとても大きくなってしまいます。
Okay. So what is the best or optimal theta and theta 1? Again, x1, again, the model and also are given. You know, we already hypothesized a model and we
とこういうふうに
a data.
少ない。
And under that two conditions, what is the best theta 1, theta 2? That is a technical issue of the regression, right? So graphically, it is a problem to locate this line to the optimal location. Optimal, in this case, is the error from the estimated data to the real observed data becomes less or least. So what is the error here graphically is that the
それぞれに対しの間で相関が高い変数というのが出てきます。この相関が高い変数というのはまだ
as the second value of the observation, which means that n is equal
あんまりうまくいかない。
and theta 0, we still don't know any idea. But at that time, real value is excellent. So when you put
I think
this is x2
こういうふう
and
にという話。これがさっきの A
theta 0 plus
プラス B というところ A と B が入っているように
and the error value is this x2 minus. And of course, there are positive error and negative errors. So we're gonna calculate the square of the error and then summing them up over n. So we will calculate error here, error here, error here, error here, 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 here. And total error is the value that should be minimized in terms of theta 0 and theta 1. So this is very simple problem, right? Because this is a quadrature problem, so-called. We well know about the quadrature function,
も
which we studied in also high school, right? So this looks a little bit complicated, but when you look at the value theta 0, which is one of the parameter, this has at highest second order, right? So if you expand this part and see the coefficient of theta 0 is simply 1 because of this.
例えば
And then you can easily plot the whole of this as a function of theta 0. And it becomes like this kind of shape, because this is a quadrature form of theta 0. Which means that there is a 1 value of theta 0, which gives the minimum
わけで
value of theta 0. So in this case, theta 0. Because of this whole, things can be rewritten in a something like theta 0 square plus blah 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 theta 0 plus blah blah blah. So this is second order equation, one second order term, quadrature form. Therefore, you can write this based on the simple math, and then you can find here Yeah, must be 2 over alpha or something. And of course, you can also calculate the derivative of this function
これやると
to theta 0. Then you can also get to this point where the, its derivative.
と x が
Right? So this is very, very, very simple problem. We are very happy. So as well as the
例えば
error value
例えば
is
値がめちゃくちゃ大きく
quadrature form of this, then the problem of finding the C1 is very easy. That's good news. But recently, in the state-of-the-art machine learning technologies, the function to be optimized, to be maximized or minimized, sometimes a bit more complicated, not like this. In that case, we need to do more, we need to do more different, approach for optimization. Sometimes it is not a closed form solution like this.
それぞれの絶対値を
It's very simple and clear. So I think you may easily understand why it becomes this, and then so easy to a minimum because that is a second order function. And of course, same things can be done at theta 1, but in that case, it is a little bit different from the easiest case, theta 1, theta 0, I
ある
mean.
んです。それに
But let me describe in a mathematical form here what we have studied in the previous slide. So the quadrature error function, when you derive it with respect to theta 0, then the derivative becomes like this. And when you put
ここに述べたような、L2 の
0, then that gives theta 0 or theta 1. And because we solve the simultaneous, we need to solve the simultaneous equation because we need to optimize two values, theta 0 and theta 1. So we also can be able to calculate the derivative of the error function with respect to theta 1, and it becomes like this.
できるというふうな
Here, it's multiplied by.
いいとこ取り
Therefore, when you calculate the derivative
こっちの性質と
with respect to
つけてやっていく
here as a product term here. So this doesn't end, but this is there. That becomes here. And then also you can say that at the minimum value of theta 1, then it becomes to 0. So when you solve this simultaneous equation, you can get theta 1 and theta 0, which minimize this value. Okay? So this is not a difficult math when you study the mathematics in high school. And also we need to be careful about this summation term. So we have to calculate the sum of this, and we have to calculate the sum of this. Theta 1 times n is equal to 1, 2, 3, 4, 5, 6, 7 until n minus 1. So you need summing up all of them. But don't worry, because
に行くのを
to sum,
ちょ
therefore,
っと
sum of the xn and also sum of n are the only things that we have to care about this summation. This is also, but in this case, you need to also calculate the sum of product of n and xn. This is different from this. And here also the n times
っていうのを入れる
n square. So you also need to calculate the sum of n square.
になって、
But you know, all those things are simple statistics, right? If you statistics,
形状で
value is calculated from the data.
るんで、ここで止まった場合、こっちの
Value or like a square mean, all those
この
is a statistic.
だけ使っていうふうにモデル
New
が得られ
a
る。
distribution data mathematical model. Then you can derive those
よく
statistics from the mathematical formula
ですね。
data. Then you can calculate all statistics.
で、まあさっき
Important thing is statistics.
それが正則じゃない
This,
ちょっとします。
the average of xn.
まあ、普通の最小二乗解っていうのがこんな形で解けますよっていうことなんですが、あ、これ x がその
simultaneous
正解値が
sum.
けれど、
Here, theta 1,
x のところが
theta 0, theta 1. So I don't know how much about
困りますよ。
about linear algebra or matrix theory. When you study the engineering, you naturally think about the matrix representation of two equations, which is like this.
なんですけど、
Equivalent.
解くっていうのは前回
Scalar product, vector, and
求める方法、この L を微分して
1.
イコール0にして解きましょうというのです。それやると、実はまあこんな感じ
and is equal to this
です
average.
が、
Okay. So this is very, very simple form. Okay. One matrix, a vector which has two components, and a vector which has two components. In other words, you know,
いうのが、まあ、この立地化
A, we calculate x.
なんで、まあまあ、今日ここで言いたいのは、まあ
Vector value B
フィッティングが
is equal
データ
so large A matrix and also large, small b vector are derived from data, and theta is a value which should be determined. So how can determine theta? It's easy. If this matrix has an inverse matrix, then you can operate the inverse matrix from left-hand side to the both side of the equation,
この問
which something like theta vector should be
題
a inverse times b.
ことができます。
So this is the solution of the optimal theta, which gives you the minimum error in terms of the square error meaning. So this is very, how do I say, straightforward, no iteration, just closed form solution. And of course, these values are very easy to calculate. So this is a very simple,
ここで言うと、
find the optimal line
こ
which fits given data. Okay, so
みたいな感じで2乗まで
problem. We assume that this value can be represented by n times theta plus theta 0. I don't know why you think that this is correct or not. That is your guess. That's your hypothesis. If you knew something, some knowledge, if you knew some knowledge about the background phenomena, then you can use that knowledge. And if knowledge tell you that, if your knowledge that x square, then you need to do something different. But in this case, the problem is theta 0 and theta 1 definition, and somehow, find this line into mathematical calculation based on the linear algebra like this.
ノルムをもうできるだけちっ答えを出したい。
simple, simplest way.
で、
you can,
構成っていうのは結局これの円の
what happened in that. Then I like to talk more general cases. Previous case was sequenced data, and the independent variable is a sequence index like 1, 2, 3, 4, 5, 6, 7, and dependent data is xm. But next time I would like to discuss about the relation between
とか、機械が
No, this is not. Let's see. I'm sorry. I'm sorry. This is again the same thing.
小さいことっていうつまりこれは誤差が多い。
Much simple case, and that is not always work because
っていうのを計算。
it's not always the matrix
それを
square matrix. So we need a more general case in which
プロセスについて説明していきたいと思います。
A matrix cannot be easily inverted. So in this case,
すごく単純で、
square
こうバン
it probably has the inverse matrix, but
その
theta 2 in
にこういうふうに
the equation should be somehow
この全部のデータを
and you
データとこのデータっていうのにします。
cases. Which is like this. So this
な感じですけども、こう
of this problem. Okay.
ただ
describe the previous equation based on much more simple matrix, not like A. Let's begin from the X matrix, which has the vector
できない。
value of 1 in each element of the first row, and value
スクローシエーションっていうやり方が、
from 0 to n minus
これはさっき
of the element in the
もっと賢い。
This is something, artificial matrix. And
特にこの交差検証というやつはこうデータを分割して処理して
row like
tenfold データ
from x0 to x,
数字が入ります。
right? So this is completely square general. But when you
具体的に何やるか
the self product
します。
this
で
then you get
学習
obtain the same form
次はこの違う3つで学習して、
by the definitions. So let me calculate.
この4分だったら4回
So
繰り返し
let's say. So this is X transpose. Therefore, from this X should be something like this. One.
できて、でそれの、平均
Starting from
全部のが多い
blah blah blah.
評価を、そういうふうなやり方があって、よく見てるの。
Then it becomes how it becomes.
このホール
Operate. Can you calculate? Let me use the whiteboard because this is very simple and fundamental. Okay.
けれども、パラメータに限りがあるときにはちゃんとした評価が、ついてないのにたまたまちゃって、誤差計算してみたらめちゃくちゃうまくいったみたいな。
What you see in here is like this. Blah, 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 blah.
すごくたくさんのデータがあって、それで学習して検索。
Therefore, for x times x transpose,
それは
it's one
もう、
zero
例えば4分割だったら4回分
times one zero and minus one. Okay?
ということで、これ
What's happened? This doesn't work.
回
Sorry.
テストがないといけない。
Or something. What did I?
いや、
Maybe so.
中型で
Did I?
終わったら4回とかでも、たまに1日かかりますとか、
X
なかなか
is like this.
だったりとかするとすごく時間がかかってしまうというような欠点もあります。たりとか生息化したりとかして、でその時の誤差が良かったとか悪かったとかいうのをこう調整していくというのが必要に。
times 1 from 0 to n minus 1. And then you can calculate the result of this product to be
なので実際動かしてみて書く
square matrix. And this and this, because 1 plus 1 plus 1 plus 1 plus 1 is a summation 1. Or from 0 to n minus 1, which becomes naturally n. And the second element is like summation of n, 0, n minus 1. And this element is this and this, therefore the same element, same number, summation n, 0, n minus 1. And this isn't square, like n square, 0, n minus 1. Okay, this is what you see as a matrix A in the previous slide. And also you calculate x
1016
0 times So then you get is summation of n, xn. The second one is summation of n times xn. This is completely same form. If you disregard the n over 1 as a coefficient, then you can get
てますが、こんな感じですね。
1. Then is equal to 2. So which means that what we get here, we denote the data in a very simple dependent, very simple form, and dependent form
になる。
because
で、この条
mean xn. Then we have two data. One data is independent and second y. General equation that we need to solve. Therefore, the solution of the theta is x inverse x transpose y. So that's what I wrote in a handout. Okay. Please remember
それでログインしていただいたら、
problem. The solution is quite simple. What you have to do is two. One is organize two matrices. First matrices is to align. One is the in this case starting from 0, 1.
実行した結果とか変更した結果は残らなくて、
It have to be such a simple
ドライブに
without data, but you can use a lot of different data.
ところにしてもらって、
And another is actually a vector which also aligns
自分でこのグループコラボですね、
dependent data.
記事にアクセスして、
Independent variable, and also second, it's dependent variable. Second
ともできます。
variable. Those data should be described in a matrix form like this in the two different matrices. Then you can calculate this for the optimal,
ドライブにコピーっていうのをコピーしますって言われて、だったら
and actually do that one of the and let me generalize this simple regression to a little bit more complicated regression type, which is the case that by the way, sorry, this is the case that I discussed in the previous slide. In this case, for the first case,
これですね、X っていうところにデータを用意していて、Y にはこの6行目ですね、ここの部分。
n becomes xn, and xn becomes yn. So these are general two set of variables, right? So this is ordered variable. This is a set of the two variables. And in the general case, you can suppose longer lines, a longer line for the polynomial, I mean, not polynomial, but hypothesized function. And also, these values are not polynomial like this.
これ見てても分かったんで、
In general, the function of the observed value xn. So in this case, function is like second order polynomial, third order polynomial, or those kind of things. But more generally, you can say that yn, dependent variable, can be calculated from the linear sum of the function of the independent variable xn. So we can put a lot of functions, as many functions as you like. And you can put as many thetas here. But still you can do the very same thing for finding the set of thetas which minimize the error. In other words, you can calculate x transpose x transpose y as a solution for theta. In this case and in this case. Because you organize the X matrix based on this, which gives you the little bit longer matrix from 2 by something,
数があるので、
m by something, because we have m terms. But still, the mathematical form is completely same. Simplest case.
そうじゃなくて学習の誤差ですね。学習データを使って誤差計算すると、こんなものです。
Case.
半化誤差
We do use the m polynomial
計算してみると、1点なのがなっている。
m matrix from 1 and 0 and x1, 2, x3.
加工式やってくれる数があります。クラスがあるんですけど、このポリノミアルフィーチャーズとなって、ポリノミアル加工式ですね。公式の特徴を作りますよっていうクラス。でこれで
1, 2, you can align
x だったときに x で
operating to these functions with x to the input. And also the dependent variable is a very simple one line. Then you can calculate x transpose times x, which is the covariance matrix, and multiplied by theta is equal to transpose y.
それがこの x っていうのが
Again, same. So what you need to do is to organize this matrix only. That's a very good.
やってみるとでどうなったかなっていうのをプリントしてみますけど x が 0.5
We need to pull up a model. Okay? Even if we can easily solve that problem, solve that equation, it is not always a good idea to use a longer equation to regress the data. For instance, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 points as an observation of the sinusoidal ideal data. If the observation is perfect, then these all 10 points should be exactly on this yellow line or green line. But because of the real world data error, we do have such an error in our observation. Then what suppose as model of describing this data?
x 3つになったこの x から
Polynomial like this. Suppose we know that this is a third order polynomial which has two peaks below and up. or first order polynomial, which is the line. These are hypotheses and these are modeling. We can obtain this based on the previous operation. If you use a first order polynomial, then the error is very big. And we cannot find the hidden structure of data like this at all. But if you use polynomial,
回帰っていうリニアレグレッションのカーブを使ってますけど、
somehow
自体が多項式
therefore
線形規定観光モデルという、それによって
this goes rapidly very, high, rapidly very.
フィッティングができます。
So as far as the area that you see here, then you can get a reasonable guess. But polynomial order function has a very extreme number when you leave from the original point here and there. So because this is a sinusoidal function, therefore this is going to be like this. It peaks. That was the real one.
学習誤差
theoretical
86と
fact, but this guess gives you a very different value when the value or independent value becomes very high or low. So this kind of things are very important to understand. What we can do is to estimate more accurate estimation by increasing the number of the polynomial, in this case 9. It's because we have 9 equations to determine the 9 parameters, theta 0 to theta 9. And also we have only 10 samples. Therefore, we can build the perfect estimate, perfect, regression like this. Perfect means there's no error. This red line is the 9th polynomial function and all
学習するという2
all the observation points. So is that good guess? No one says it is. Because it's a big error here, big error here, big error here. So this, when you observe this point, then error is like this. When you observe this point, error is huge. So this is really the problem of the overfitting. This overtunes to the particular observation data. So when you increase the number of the observation, what you will have is a misery. So please be careful about to use too many flexibility for modeling the system.
でリニアレグレッションをするっていうふうに、実験数を増やして
You can increase the data. Whatever you do, data science. Every time you increase the data, you get a better result in any means. So the same thing can be applied to the case that we have 15 samples. Then the extreme value becomes less. And when you have 100 samples, which has, each of them has a big error here, there. But if you, apply the 9th order all those data, then it becomes very close to the original sinusoidal line. Okay? So always it is a good idea to increase the data for training. That gives you a better result. Please do not hesitate. Please do not hesitate to collect more data. So even if you have a big flexibility like m is equal to 9, if you have data which is sufficient to train the system, then you are free of the
さっきラスト次回期って言ってましたけど、
millions of parameters, right?
リニアレグレッションっていうのも
Parameters. In this is the case, just only 9 parameters, but millions of parameters. Imagine that we need to have trillions of data in order to do a robust, stable estimate. So
L1 生息化とか L2
important.
を、導入することができます。
And even we do not have enough data, there is several good ideas to avoid the overfitting. Ideas are called generalization. This is another very simple idea and very well-known idea. For instance, because this is that we defined as error, this discrepancy from the real data and estimated data, squared and summed. There's no regulation on theta value. When you add this term to this error value, then what happens? Of course, the system trying to decrease the number of this error, value of this error. But on the other, if the lambda is big, then efficient to use
もうちょっとタイミングでやっていいかなっていうので、時間が
So does this mean? This means that in rough meaning, how many theta are efficiently used for estimating? For instance, suppose that okay, let's discuss about the 9 polynomial case, and therefore we have 10 thetas. And if the value of the ninth theta, theta 9, is 0.0001, and thetas are also very small value, but only theta 0 or theta 1 has a big value. This value becomes very small. Comparing to that, all those 9 values have a significant number, like 1, 5, 3, 2, 5, something. So, the case that I mentioned,
関数として
like theta 0 and theta 1 has significant value, and the other value has a very small value. It's the case that this value becomes very small comparing to the free, valued case of the theta. And in that case, the estimation of the system would only use, the first or second estimation. So suppose that this and this are very big and these numbers are very small, then even we use this who are also
ある回はこのデータを使って学習してこのデータを
really important values that this and this, therefore equivalent to use the second
そういうことをやってくれる
linear regression case. And in that case,
ホールドっていうやつなんですけど
square is small.
数5とかいうふうに
And if you use all thetas, then it actually becomes like this. In that case, theta square is big.
テスト用暗号っていうのを
So by putting optimal lambda and summing the square of the theta to the error term, then we can somehow control the complexity of the model.
テストインデックスっていうのでした
Compromise
だけを使って今日
like this. If lambda is equal to 0, which means that generalization term
に入っているこのデータだけを取り出して
big,
失礼しました
lambda is equal to 0. But if the log of
こうやっ
lambda
て
is
デ
minus
ータを分割をして 得られたこのデータですね。このデータっていうのを使って、例えばを学習して、で、データを使って、このループの1回の誤差を。
When you increase the lambda value, then the model
大体書いてますが、
for the test data,
足していって、平均取ると答え出ますので、
the lambda,
参考
the parameter for the training
にしてもらうといいかなと思います。
data becomes better and better. But on the other hand, for the testing data, we get a worse result or miserly result. But the model complexity is somehow controlled by lambda value.
実際ちょっとこの
Discrepancy
で試してみます。
model training and testing are not so big. We can find some compromising by repeating the test using the different lambda value. And probably that is like this. So you better to use this kind of, this value, this range of lambda for the result. So robustness model controlled by the regularization term. And 5 years ago, learning or machine learning field, but currently they say regularization is not so much important like we saw before, but increasing data and also executive search meta parameters can overcome the difficulty of finding the robust modeling. So the state-of-the-art technologies that seems, we need the trade-off between the or training data error and test data error, or robustness, or number of the data. Those things very important for their applications. Unfortunately, I have only 20 minutes, so I need to move to the next topic, but cannot go in detail. But I like you to know also about the sequential data. How can we deal with that? Because if you do natural language, if you do image, if you do social, statistics, the time sequence data are not so much important for you in some cases. But actually, the time series data in a physical observation is quite important. So I like to briefly mention about basic technologies which has been applied to the sequential data. Again, the same or very similar equation here. Yn, theta 0, theta 1 times phi 1 xn. This was the regression equation. And suppose that Yn is equal to xn yourself. And xn operated by phi 1 is xn, means that this operation is the delaying operation of data. And theta n times phi m is also. Then this is relation prediction that the previous data you're going to regress. Okay, so this is regression data. This is slightly different that we started. Then when you you can actually write this system like this. That is not important. Okay, so time sequence is kind of a problem. And same as the previous cases, we can write two important matrices. One is the simple matrix, which align the original data. And in this case, the operation was time shifting. Therefore, the time shifting is shown here in the rows. And this is another data, which has one sample before these kind of things. Then you can calculate the T transpose times X, X transpose times X, which becomes the shape like this, 3 by 3, a regular matrix, and a rectangular matrix, and this is known as autocorrelation matrix. But anyway, this is the same thing, and this is also the same thing. Therefore, you can easily solve this linear equation and by the same name. So like this, okay. So by this operation, you can define theta. Actually, this operation is known as a linear prediction of the time sequence data. And this was important process of predicting the you use a cell phone. You not so often talk to them, but when you talk to cell phone, all speech are compressed and send it to the your body. The compressed mean that original speech size will be somehow reduced to the particular for the particular use of the telecommunication, and this method is fully utilized for that data compression, and actually invented here in our university and used in worldwide all cell phones. And yeah, this is a typical topic talk.
さっきのグラフはここの部分が拡大されて表示しているみたいなんですけど、
I briefly talk about random process, but the random process is a random variable or set of random variable or ordered random variable, which individual numbers are random, and therefore it is defined by a distribution function. By the way, this is a complicated term, so let me graphical understanding of the random variable. So when the random process is given, it process not always give you the same value of the sequence. Like this. Say, for instance, this is the average temperature of a day from the summer to autumn, okay? So generally, in summer, the average temperature is high, and in autumn, lower. But it's not always the case. That depends different on year to year. So this is 2018, this is 2019, this is 2017. Then the global trend that summer is hot, autumn is cool, is preserved in every year, but the observations are completely different. Okay, so those are the very typical case of the random process. Okay, and we can calculate the average. What we can do is to align the change of the temperature in every year. Okay, so a plus symbol is the 2017, and circle symbol represents the 2018, and X symbol represents 2019. And you can calculate the average at every day, every individual day. Then you can get this smooth line as the average. This is quite look same like the previous denoising process. But in this case, average is 0. But this sort of average smoothing is quite easy to get know the
でそうすると、学習の誤差は 0.96 なんですけど、この半化誤差ですね、さっき500何とかあったのが、1.3 ということで、かなり
the model of the global change of temperature.
感じで、
So simple averaging again works for estimating the global trend. And another topic is discrete sequence. So what discussed in the previous slide were, not a discrete but a continuous sequence of temperature. Well, we can also discuss about the sequence of symbols. Okay? For instance, the word sequence. 今日私は学校に行った。Suppose that the probability that happens 今日私は学校へ行った is very probable. You are comparing more probable comparing to that 今日私は学校空海 That sequence of words are not so frequently happen. Or 私今日は学校行った Those are different terms of the data. It's also very rare or improbable. So the probability of the sequence is another very important characteristic of the sequential data. But it's very difficult to estimate this whole sentence probability. How do you define or how do you calculate the probability or actual probability that happens 今日私は学校へ行った or 今日学校私は海空 There's no way to estimate the probability calculation the probability of those two different sequences. But with all Japanese text from the web, sentences,私は学校へ行った It's not realistic that to do all the sequences history of word sequence. And the idea that we usually use is to calculate or to assume Markovian property. It's a good property that we can forget the day before yesterday. Markovian process only depends on the previous case. In this case, 今日私は those two words are important. And we can calculate the probability that 私は happen after 今日. And whatever the other part of the sequence would be disregarded. So then we can calculate this value. Of course, this value cannot be representative to this, but when you do the same thing for the third and fourth word, then you can calculate whole this sentence by chain rule like this. So this is through omega W1 times P2 given W1 times P3 given W1 W2 times W4 given 1, 2, 3, or W5 given 1, 2, 3, 4. This product may give you the accurate value of this, but when you suppose the Markovian property, then you can forget this, or you can forget this, you can forget these, because of the Markovian process property. So you only remember the one previous case. And of course, it becomes nearly equal, but this works. Of course, you can remember two previous cases, or even three previous cases, and use that characteristics. I heard that Google uses this kind of sequential combination, and it memorizes every three occurrence of the 4 or 5 sequential data. That gives you the very long history Markovian model. But simplest case is simply remember the last one. And using this, you can calculate very long word sequence. Sometimes call this unigram. Bi and tri is in the Greek Latin numbering thing. So trigram means that two words preceding to the nth word can the or so 私は is very probable, but 今日私山 is very improbable. So this kind of local dependency of sequential data can be used for calculating even very long sequence of the random process. This is the good point of the random amount of the sequence. The word count gives you a good estimate of this bigram probability. In other words, you calculate and all combination of two words starting with kyo. And then also you calculate the particular word wa precede or follow to kyo wa. So count the number of the kyo wa and take the ratio against the kyo and other words sequence. And this is very big number, and this is a very small number. Therefore, the bigram probability usually are very small. And problem of counting the word sequence is like this. If you have not sufficient, if you don't have sufficient, again, big database, the count of the word in particular contexts are very rare to be seen. Therefore, if you based on the if you estimate the probability based on the occurrence, then even the case that you never seen in the limited number of text or database would be estimated as 0. Never happen. But it is not a case. Because that never happened doesn't mean that, never happened in the previous, never happened in the training database doesn't mean that it never happened. it happens. But the database is not appropriate or too small. Therefore, we need to somehow smooth these particular values, which is called counting operation. So even you have 100 times, 90 times, 50 times, you pick up, say 5 of them from this count and distribute those data, which discount these observed and which increase or virtually distribute the account to the unseen data. So this is another robustness. This gives you another robustness of the estimation of the sequential data when it is a discrete symbol like a word. So actually, this discounting one, this prediction looks completely different from each other, but actually, they, in some sense, related, but they're not in that detail due to the time. Might talk today. Today, first dedicated to regression analysis, we assumed a very simple model and then expand it to the general case. And finally, you found that x transpose times x inverse and multiplication to x transpose y gives you the optimal weight of the theta 0 or theta. That is very simple and common structure. And those things are called linear regression. And second topic is the sequence. And we can use linear prediction. We can use the Malkovian modeling of the probabilities of the sequence of the discrete symbols. This is the end of my talk. And if you feel arrived, please come to me, or you can also try to put it that I captured last year. But yeah, I'm happy to answer to your question when you have any question. But please look at it. I am
成熟化っていうのを紹介をします。
not so in my time at the desk. So, but anyway, thank you very much for coming, and please enjoy the exercise that's going to follow this lecture. Thank you very much.